This webinar is now broadcasting to all.
Okay, so we are live with everybody. So everybody, welcome to the SPEE webinar on Subsurface Analytics. Today with us we have Shahab Moheggi. Did I say that right?
Moheggi, yes.
Moheggi. Shahab is a professor of petroleum and natural gas engineering at West Virginia University and the CEO of Intelligent Solutions, Inc. And with that, sir, I will turn it over to you.
Thank you very much, Mr. McCown. Hello, everybody. I can go ahead and get started, or probably it's 12:01, so I'm going to wait another minute or two as the participants are getting on. We have 63 right now. So let me go ahead and start sharing my screen. Okay, so I'm sharing my screen, and please if you have any questions, please type it in, and at the end I will go ahead and try to answer any question that might be there. Okay, so it's 12:02. I'm gonna go ahead and start the presentation. Very well. So thank you very much for attending. The topic's title is Subsurface Analytics, Application of AI and Machine Learning in Reservoir Engineering, Reservoir Modeling, and Reservoir Management. I'm going to start by letting you know what is it that I will be covering as far as this particular webinar is concerned. Subsurface analytic is applicable to both conventional resources and unconventional resources. In conventional resources, it has two applications. One is only to mature fields. That means the data is already there. There is a history. We call that technology top-down modeling. And the second one is called smart proxy modeling. And it is the smart proxy modeling. It's a proxy of numerical simulation, numerical reservoir simulation. Therefore, it can be applied to both greenfield and mature field. I'm going to provide examples of both of these cases for you. In unconventional resources, also there are two applications. One we call Shale Analytics. And Shale Analytics deals with completion and production optimization. And the second application, which is something that is happening today in terms of research mostly, is dynamic shale analytics. And that has to do with reservoir simulation and modeling of shale analytics purely based on data, which is a bit different from, not a bit, but a lot different from how the regular data-driven reservoir modeling works. I'll explain that. And the reason we want to do that a lot today, it has to do with frac hit, which is a very important issue associated with the unconventional resources, like the shale assets. And I want to show you how this technology can be used in order to predict and mitigate and manage frac hit. With this, let me start by providing a definition that subsurface analytic is a physics-based simulation and modeling, but it's a non-traditional physics-based simulation and modeling, and I'm going to be explaining that. The question is how physics is modeled in subsurface analytics. It is modeled through field measurements, not through equations. It is modeled by avoiding any major assumptions or any major simplification, which is the key to a very lot of numerical modeling that we do in our industry. And another one, it's based on knowledge of domain experts, which is a very, very important. In other words, if you are not a domain expert, if you're not a reservoir engineer, then it's going to be almost impossible for you to do subsurface analytics. But there are situations where the AI experts get together with reservoir engineers and together work on this. That has a possibility of success. One thing that I need to mention is subsurface analytics is data and knowledge fusion technology. This is a definition that we came up with actually at the late 1990s. It's not a new thing, this data knowledge fusion. You can see it in some of our publications. So, and the main difference between this and what some other uses, it is not a data and equation fusion. That's completely what some people call it hybrid model. It's very, very different from subsurface analytics. That's something completely different. We can discuss it if anybody has any question, but that is not what I'm referencing to subsurface analytics. It's data and knowledge fusion. And another key issue about subsurface analytics is it is based on explainable artificial intelligence. This explainable AI, also known as XAI, which DARPA is doing a lot of work on it, it's something reasonably in the context of AI, it is new, but in the context of subsurface analytics, it is not new actually. And I will show you why am I saying this and what is the actual results that I can share with you, and you can see what I mean by that, but we'll move forward with it. So I'm going to start by talking about the engineering application of AI and machine learning, and of course go to subsurface analytics in conventional and then in unconventional. And if the time permits, I'm going to talk about petroleum data analytics, which is the key behind all of that, and we move forward. So let's start with engineering application of artificial intelligence and machine learning. Modeling physics through facts and avoiding assumptions and simplification. So prior to that, let's do a definition of these technology. What is artificial intelligence? Artificial intelligence is the technology that mimics human brain in analysis, modeling, and decision-making. Machine learning is use of open computer algorithm. One of the things you will, when you start working in this area, you'll find out that you do not model directly and explicitly, you do not model the reservoir. What you do, you use the data in order to train an open computer algorithm so it can learn reservoir engineering and reservoir management related to the model, to the specific case that you are working with. That is the main difference between how this technology works versus numerical reservoir simulation. When you do numerical reservoir simulation, you model everything very explicitly and very, 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 very detailed. You tell the computer exactly what you do. You have come up with not you necessarily, but our industry have come up with an equation of diffusivity equation, and then you model in so much detail that at every few square feet, how to explicitly what the computer program needs to do in order to build the model of the reservoir that you're dealing with. That is not the case in machine learning. In machine learning, the software that you use is an open computer algorithm that can be used for so many different reasons and different types of problem, what you're doing, you are getting data from your system in order to train that open algorithm and make it learn what you're trying to teach it. Machine learning requires teaching in order to learning to take place. So what you're doing, you're teaching a system, a machine that can learn. And the key is the definition of subsurface analytics literally could be teaching reservoir engineering to an open computer algorithm. That's literally what it is. And the other one is deep learning, which is a pattern recognition using artificial neural network. But again, it has to do with artificial neural network more than anything else. This is not something I want to go into the detail of it for the short period of this presentation, but at least these are the definitions that you can have. So there are differences. One of the key issues that why we talk about AI for machine learning and machine learning for engineering is because there is a difference between engineering problems and non-engineering problems. When you're solving a non-engineering problem, what you require is general intelligence. And when you're doing non-engineering problem, what you do not require is domain expertise. We'll talk about that. However, when you're dealing an engineering problem using AI, then it requires domain expertise depending on what domain has you're dealing with. I'll give you an example. Here are the images that you see between cats and dogs, right? In 2005, 2006, some scientists, AI and machine learning scientists, came up with convolutional neural network, and what that really does image recognition. And the question is, don't get me wrong, I'm not saying it's simple at all. Actually, in many cases, it's even more complex than engineering problem solving, to keep that in mind. However, the key is its general intelligence. In order to identify the differences between cats and dogs, you do not need to have a bachelor's degree or a PhD. A 5-year-old can tell the difference between a cat and a dog. So that's why it's called general intelligence. It's called human level intelligence, not a engineering level of domain expertise intelligence. Another example, these are the examples that you deal with on a regular basis all the time today. Face recognition, right? That when you use your iPhone in order to open up for you, it recognizes your face. Well, your child can recognize your face. Your friends can recognize your face. It doesn't require any domain expertise. Object recognition, which is used that identifies between pedestrian versus cars versus trucks versus bike. Again, you do not need a bachelor's degree or a PhD to find out which one is which. A 5-year-old still can do that. Voice recognition, you do not need, again, domain expertise for that. General intelligence can handle that. Even autonomous vehicles, the way it's being dealt with, it is general intelligence. People who drive trucks, people who drive cars, they do not need bachelor's or master's degree. Even if they cannot read, they still can drive. The next one is translation. And again, you do not need domain expertise. The kids at their 3 or 5-year-old, they can speak multiple language when they are in a situation that mom is from one country, dad is from another country, and they speak to that child in different languages. And a 3-year-old can speak 3 different languages. This is actually my niece's child. I can see that clearly. Another one is the caption generation, using LSTM, the long short-term network that was generated. It was not generated in order to do what some people today do in our industry, using LSTM to literally generate what's very little different from decline curve analysis because they deal with the time series. Well, where did that came from? That technology came from, it was developed to caption generation of an image. So if you show an image to a 5-year-old, can the 5-year-old tell you, oh, that's a bird that's flying over the sea? So you do not need domain expertise for that. And that's the difference between engineering versus not engineering. Now, let me give you another example. Here you see two series of dots. You see yellow dots and you see black dots. The question is, if I ask you to draw a line that can separate yellow dots from black dots, can you do that? The answer is yes. It's very, very simple. Even a 5-year-old can do that. Correct? But that's a non-linear separation. However, what if you ask that 5-year-old that I want you to separate these, but I want you to do a linear separation? Do you think still a 5-year-old can do that? No. Because in order to do that, you need to know the mathematics. Once you do the mathematics, then you can separate them using a linear separation. That is the type of domain expertise that is required, and it's different from nonlinear separation, from Another item is throwing an object to be caught by another person. This is an engineering approach whereby missiles are developed. With that. You need to know initial velocity, you need to know the initial angle, and then in order to find out the range, you can calculate it. Do we solve this kind of problem? Does human brain does that? Yes. If you watch football, American football, you can see that that happens all the time. I give you another example. Balancing a stick on the palm of a hand. If you do that only in 2D, imagine that little car moving back and forth, and it's going to balance this. Can this be engineeringly taken care of? Absolutely. It's going to be quite complex, but it can be done. Can human brain does that actually in 3 dimensions? The answer is yes, a 5-year-old can do that. So human brain does solve engineering related problem as well, as you just saw it. But the question is, how does human brain solve this kind of engineering related problem? Does our brain build an equation and then solve it in order to find a solution? The answer is no. Our brain does not build an equation and solve it. So there is a different way. Our brain uses its neuron by observation and experience and trial and error through dendrites and cell body and axon in order to even solve engineering related problems. So if we're going to mimic human brain to solve engineering related problem, we do not need to build an equation. We can use observation, experience, and trial and error, but domain expertise plays a very, very, very important role in order to do that. Engineering related problems, how important is domain expertise? How important is expertise in the application of AI, and how important it is the fundamental knowledge of AI and machine learning. In my opinion, 50% of that expertise must have to do with domain expertise. The other 50%, to a very large extent, should be to become an AI and machine learning practitioner, not necessarily fundamental knowledge, but if you want to do research and not necessarily only practice it, then you need the fundamental knowledge of that as well. So there are a major difference between the application of AI to engineering and non-engineering related problem. That is the key behind what I wanted to communicate with you. And one of the major issues is some people, unfortunately, that's when this is communicated with the engineers, a lot of engineers think because they're engineers, one thing that they've learned at the university during their BS, MS, or PhD is that in order to figure out the physics of even a very complex problem, they need to learn the mathematics behind it, which is a very, very correct thing. However, that's why some of the engineers also think if they know the mathematics of machine learning and AI, then they become experts in AI and machine learning. That is very, very incorrect. That is why people have come up with so-called hybrid models, because they learned the neural network and some of the fuzzy set theory and genetic algorithm, and they looked at the math of it, they learned the math, and because they understand the mathematics of it, then they're done. Why? Because that's what they learned when they were an engineer. But that is not true, because the math behind AI and machine learning is incredibly simple. You don't need a BS degree or a PhD in order to understand the math. I've taught it in many other areas. We don't have the time to go through it, but it's an incredibly simple mathematics. So it is not about mathematics. It is about philosophy. It is about a completely different, it's a paradigm shift on how you deal with the problem in order to solve it. If you're still thinking the way you've learned in engineering, so the domain expertise that I'm referring to when I say engineering it's not really about math. It is about the approach and the knowledge of engineering, not the mathematics of it. That's why you need to shift your problem solving of engineering, going from mathematics to philosophy and to neuroscience and to computer science. Don't get me wrong, you still need statistics and mathematics and biology to learn to do that. But the key behind AI and machine learning to solve engineering related problem to a very, very large extent is philosophical, and the approach is different from what you've learned during your bachelor's, master's, and PhD if you were a petroleum engineer or any other engineer. You have to keep your knowledge, not the traditional approach to problem solving. That's really what I mean. So with that introduction, let's talk about the subsurface analytics. I'm going to talk about these four technologies that I mentioned. First, two of them are in conventional resources. The first one is top-down modeling, which is an AI-based reservoir simulation and modeling. This is for conventional resources and mature fields. Its definition is it's building purely fact-based and a simulation model, but that simulation is a combined, coupled reservoir and wellbore simulation model, not a purely reservoir model. That's why we do not need to have flowing bottom hole pressure for top-down modeling. That you do need it for numerical reservoir simulation, but you do not need it for top-down modeling. You need wellhead pressure and choke setting. So the field measurements that you use for top-down modeling are well characteristics and trajectories, formation characteristics, cores, logs, and everything that you have done is actual measurement. The seismic attributes directly can go and contribute to top-down modeling. Completion and workover, operational conditions at the well, at the surface, not at the reservoir, because you don't have those measurements. You hardly ever have more than a few measurements of bottom hole flowing pressure, and of course production history. One key issue about TDM is that it's fully automated history matching process. For those of you who are familiar with the history matching in the real world, not academic, what we teach you at the university, which is everything is put in a very simple fashion for you to learn the process. But after you've done that, you go and work for a company or a service company or operating company or consulting company. Then if you have actually dealt with the real world situation of history matching in numerical reservoir simulation, you find out that to a very, very large extent, everything about the modification you make around the wellbore or to the wellbore in order to achieve history matching. You do not need to do that in top-down modeling. There is no well-based modification to achieve history matching in this process. Another key thing that you should know when you're doing a real-world situation, oil production in numerical reservoir simulation during the history matching is used as an input, not as an output. That is not the case in top-down modeling. Oil production is not used as an input during the history matching. It is used as an output. And one last thing, it's One of the things that some people that have recently started for months or a couple of years doing this, they come up and they build a model on a per well basis. If you have 100 wells, then they build 100 models, one for each. And that's one of the ways they use that LSTM or recurrent neural network. Well, that to me, that is literally what you're doing is decline curve analysis in a very complex fashion, but it's really not a numerical reservoir simulation. That's the main difference. The top-down modeling makes one single model that applies to all the wells from 10 to 100 to 500 wells in your field. One model, a history matches every single well in that model. Another thing is blind validation in space and time. You take the tail end of the data. I will show you a bit more on that. You leave it out in order to validate your history match. And TDM deployment, it forecasts it in the future. And forecasting and production optimization, once you build the model and validate it, then you use it for production forecasting, then you use it for operational optimization, such as choke setting, gas lift, injection of water and gas with CO2, or for CapEx optimization by infill, identifying where to drill the next well. The process is you use the well placement and the reservoir characteristics and the completion, details of completion that changes as a function of time in reality, and the hydraulic fracturing or any other workflows, then workovers, sorry, and then operational conditions, and then all of that comes and give you the well productivity on every single well basis. There's 3 steps to it. The first step we call descriptive analytics, where you do well biography and you do well performance analysis, you do key performance indicators. That you deal a lot with the data. That takes more than 50%, sometimes even 70% of the entire project time. And then you do the predictive analytics. You build a model. You have to deal with the architecture and topology and hyperparameters of the model you're trying to build, the learning algorithms. You have to try to avoid memorization and do blind validation of it. And when all of that is done, you validate it and you feel good about it, then you can use it in order to perform optimization, which is prescriptive analytic. You deal with uncertainty quantification, well performance prediction, infill location, choke setting, injection, recovery, plateau, blah, blah. All of these can be done after you've done the predictive analytics called prescriptive analytics. So in order to go, I don't want to go into too much detail of that. I've written a lot of, anyway, whatever we do in TDM, unlike others, we do not tell you that we cannot share you the details of how we do it. I have written a book, all the details are there, everything. We are very, very transparent of every step that we take, and we do it so you can actually follow and do exactly what we have done. This is, I'm going to show you the results of a paper that's going to be, has been already published in ATC 2020, but it's going to be presented in October. It's a subsurface analytics for a particular field in Malaysia. So this is the field, it's offshore. It's a very, very complex field in offshore Malaysia. They literally for many, many years, almost a decade, tried to use conventional numerical reservoir simulation to build and history match this model for the entire system. It never works. That's why we came in to do it. It has 4 platforms of A, B, C, and D, as you can see in different colors. And these polygons separates the different wells drainage area. That's not drainage area with the definition of well testing. It's a drainage area, but it's a completely different definition. It's in the book. I don't want to go into the detail of that unless you have a question. I'll be more than happy to show it. But as you can see, there's oil producer, water injector, gas producer, and gas injectors in this particular field. It's about more than 200 wells that we were dealing with. This shows you the production records that we have for each year from all of these wells. And as you know better than I do, that when you deal with a real situation, not all 200 wells are drilled at the same time at the beginning of the field. It takes time and more well. There are multiple phases in developing new wells, and each well then provides you with information. And from 1991 to 2017, this is how many records we had for the entire field. And one of the things that was very important to us was to have a wellhead pressure, wellhead temperature, and choke setting. And this shows you what % of choke setting, what % of wellhead pressure, and what % of wellhead temperature was available for these fields from 1991 to 2017. And you can clearly see that you never have, in reality, one of the things people always ask, that when you deal with the real world situation, how do you deal with the data? Because data is not certain, it's not 100% correct. Of course, we know that, and there's a lot of data missing. How do you deal with it? Well, there's a whole part of the top-down modeling that deals with that. And again, the key is, unlike some others who do it and call it hybrid modeling, when we do not use any equation which is based purely on a lot of assumption or examples that have been done in the laboratory, but then brings to the field and apply it there. We do not do that. We use it purely data driven. And from 80% in 1991, you go down to less than 10% in 2001 for these wellhead pressure and choke setting. And temperature was not even started measuring until 2003. And the amount of missing, you can see that there's a lot of data missing, but still, there's a whole process that goes during the descriptive analytics that you deal with the missing data in order to move forward. It's a technology that we can deal with it and talk about it later as we move forward. Top-down modeling uses static and dynamic field measurements for the focal well, for the well we're dealing with, and for offset wells, and it brings them all together. You literally build a model for wellhead pressure, one for oil production, one for gas production, one for water production, one for reservoir pressure, and one for water saturation, and you connect them all together. And for every time step, all these models, every single, for example, oil production is a model for oil production, but it deals with the entire 200 wells, not necessarily only one well. And as we move forward, you can see these are the levels that build the top-down modeling. Another thing that we do, we use fuzzy pattern recognition, and we generate what we call reservoir conductivity map. And then we use it in our model as well. This reservoir conductivity map is not a plot of the permeability. As you know, probably as domain experts better than I do, that reservoir conductivity is not only a function of permeability. Permeability plays a very important role in it, but it has to do with porosity, it has to do with thickness, it has to do with, these are the static information, it has to do with dynamic information as a function of time, it has to do with saturation, it has to do with viscosity, it has to do with the pressure that has been used in order to produce oil and gas and water. So you take the history and find out, based on all the production and data that you have, how this the conductivity maps throughout the reservoir. And you can see, when you see the top big one is for the entire reservoir, but you can actually do that for groups of the layers. As you can see on the X is groups of a few layers in X and Y and Z, and there's more of them, of course, for this, that shows you the conductivity map of this reservoir before you go to the top-down modeling. One more thing before I show you the result is the data that we receive from the mature field, from today all the way back to the initial production date. This is the entire data. When we do that for a project, we do not use all of that data to build our top-down model. The first thing we do, we identify, we take a part of the data from a year before, 2 years before, depending on the model we're dealing with. We remove that data from the piece of data we have that we received to build our model. That part of data is not going to be used to train, to validate, to train, to calibrate, to test the model. It's put aside. We use, then we take the rest of the data and we divide it to 3 parts. One part of it, which is literally 2 parts of it, is used for training and calibration, and the end part of it, we call it blind validation in time. So we use the data for history matching, let's say from 1991 to 2015, and to history match and calibrate and figure out when to stop memory, make sure that the system is not memorizing. Then from 2015 to 2000, let's say 17, we use it for blind validation. And from 2017 to today, after we built the model, we do it purely in forecasting, and then we'll compare it to see how good our model is. That's how we develop the top-down model. And this is a good example for the entire field. What you see in dots are the actual data. The line is the TDM, the top-down modeling result, the history match, and you can see the blind validation, the forecasting on the right-hand side was the part that I mentioned we removed from very beginning. And just to give you a bit of more detail, so here's a better look at from 2005 all the way to 2017 to what we have dealt with. So this is for the entire field, and this is for the entire field for gas-oil ratio, actual versus TDM, and water cut, actual versus TDM for the entire field. But the reality is the actual TDM is not the reality is that we have dealt with this. We don't do it for the entire field. We do it on a well-by-well basis, and then we history match it, sorry, on a well-by-well basis, and then we sum it, and you get the results for the entire field. You can then sum all the platforms, the 4 platforms that we have. You can sum all the wells in one platform and see the result of the entire platform. 1, 2, 3, and 4 platform as we have it. But the reality is we'll do it on a single well basis, not building the model on a single well basis, but testing it on a single well basis to make a judgment whether we have a good top-down modeling or not. For example, this is one of the platform, and this is one particular well in there, and we have 2 years of blind validation forecasting for automated history matching, and you can see we have 6 simultaneous dynamic variables. This is the model that we built that uses the choke setting and tells you what the wellhead pressure is going to be. The dots are real data, and the line is the top TDM. This is for the same well for oil production and for the gas production. And again, the same model does the same thing for multiple wells. And this is for the oil production. And of course, you can do it for water saturation and reservoir pressure. And again, the dots are the real, the line is the TDM. And then we do that for blind forecasting, as I mentioned, the data that was removed and not used in order to dealt with. The data that you see in red was not used to build the model. It was only used to, after the model was built and history match, to see how good it was for the forecasting the future. This is for specific wells in one of the platforms, and the result that you see is the results of the TDM for this particular field. And of course, we can do a long-term production forecasting using the TDM. This one has been done, this is for the entire field for 18 years all the way to 2035. This is oil on top and water and gas in the bottom. But the reality, as I mentioned, we do that for every single well, and then we sum it, and then you get the result. Same model does it for all of them, for every single well. And you can see here the 18 years of forecasting for oil, gas, and water for a single well. And this is for another well. And again, we do it for all these wells and sum it together, and you see what we have. So that said, that was an example of one of the most recent work that we have done. I'm going to show you another thing that has to do with validation, field validation. This was a field called Buhasa with ADNOC that we did in 2010. And when we did that, we finished it in 2010 and 2011 actually, and then 5 years after they came back, they said, okay, we want to find out whether the model that you built for us 5 years ago is good enough. They wanted to give us another project, and we had to validate it. So what they told us, since then we have drilled 23 wells, and we're going to give you the location, and can you tell us what was the pressure and the saturation of the location where we drilled the well for this new wells that we drilled, these 23 wells. And here's the results. We call it stress test. This is 5 years. The model was not even updated. We used the model that was developed 5 years ago, and there was 23 wells. 2 of them was in different layers of the reservoir, A, B, C, H, I, 23 of them, and this is the results of the pressure that we got. We found out that 35% of the wells, our predictions were more than 95% accurate. 26% of the wells, our accuracy was between 95 to 90%. Another next 30% was between 90 and 80%. To sum it up, more than 90% of all the prediction that was made by TDM 5 years after the model building, looking back, it was 80%, up to 80% accurate. Same was true for water saturation. We did that. We found that 40% of our predictions were more than 95% accurate. And you see the rest of them, literally 70% of all the predictions that made by TDM were more than 80% accurate for this particular field. This is another field validation for another field in the Caspian Sea. One of the things we did after building the model, we did production optimization for them, and we told them what to do in terms of choke setting in order to get more pressure. And they had 2 series of platform. One was low pressure, one was high pressure. 3 wells that were in high pressure, we told them to change it to the low pressure. Actually, we did that for more wells. I did 3 wells. They actually did not only test, but they opened it and they went beyond the testing and actually did it. And they found that 190 barrels per day enhancement of oil, incremental oil production based on our recommendation. And then what happened is literally, we made sure, of course, you do that, you have to make sure that gas oil ratio, water cut, and pressure, that you don't want to overwrite those. You open the choke to a certain amount that it does not undo or does a bad thing for gas oil ratio and other things. So actually, and then there was the 2 locations that we identified that new wells will be done, and then we'll find out that one of the locations, there was another well actually very, very close to one of the locations that we had already identified, but we didn't know about it. They tell us that it's an email that was sent to us that we would like to inform you that that well location there was very, very good well that you provided. And this was this choke setting optimization. We made 15 particular predictions and recommendation for optimization, and they tested them and found out that 13 out of the 15, which is 87% of our predictions, were correct. And the 3 of them, as you saw, they actually did it. And the same field, as you can see, we have blind validation, history matching, and what you see in the forecast, which is the yellow background, that was we didn't have the data when the time for that project was done. We only provided the line, and then they actually went and identified the actual data, and it shows you how good or how bad, depending how you look at it, was our predictions of these particular wells. The blind validation that we did was, as you can see, is shown here, but also the forecast, we had no data when we did that. And it can show you how was our prediction compared to afterwards when they did analysis. So that gives you an example. This is what we did for top-down modeling. The next thing is a smart proxy modeling. What smart proxy modeling is, it literally, what it does, it provides you a tool to build a proxy model for numerical reservoir simulation. So it doesn't tell you whether your numerical reservoir simulation is correct or wrong. It just builds a model of your model. The data comes from numerical reservoir simulator. The only difference is you can run it 1,000,000 times. You do not need to, and you can do it on your laptop rather than HPC. So smart proxy modeling is a complete paradigm shift in how to build a proxy model of numerical simulation. It replicates the results of original numerical simulation with very, very high accuracy, you can see in a minute. Then it does it at the grid block level. Do pressure and saturation changes at the grid block level, not only at the well level. You do it at the well level as well. It decreases the computational footprint by orders of magnitude. You can make tens of runs in your laptop, on your desktop, but hopefully very soon you should be able to take your Eclipse model or CMG model or a T-Navigator model that takes literally a whole day or 10 hours in an HPC to run. You can build a smart proxy of that, and hopefully very soon then you can use your Eclipse and run it, or your CMG and run it on your smartphone or on a tablet to get the results almost immediately. So in tradition, well, we knew that there's traditional proxy modeling back. Why we did that to begin with, because we wanted to. It takes so long to run the numerical reservoir simulations. But the traditional proxy models are two of them. One of them is called reduced order model, which it simplifies the physics, or it reduces the resolution. It makes it larger. Grid blocks, and the number of time steps becomes small in order to, you reduce the order of the model in order to do that. So you're literally solving a different problem. Or you can use statistics, which is called response surface method. And again, that is it's a curve-fitting process. It's the difference between statistics and machine learning. It's very, very different from one another. And it's mainly based on, you don't do response surface for the entire field and for the entire, every single grid block. You do it for wells sometimes. And then again, you need hundreds of runs, and not a lot of time it doesn't work very well. You know, if you've done it, you know better than I do. But a smart proxy model is teaching engineering problem solving to open computer algorithm that, as I mentioned, using the data that comes from a numerical simulator. This open computer algorithm includes a series of machine learning algorithms, and the numerical simulation data that you use are the data that is used to build the numerical model and the data that's generated by the numerical model. And in order, a numerical simulation of a complex series mathematical equation that you have, that's why you have to solve it numerically. So examples of smart proxy models, we have well-based, which is very much close to the TDM that I showed you, or cell-based, which has to do with the single cell, even if you have 1,000,000 cells. In the cell base, you can apply it to numerical reservoir simulator, which I'm going to show you. We have, this is the first technology that was developed in the oil industry, and now it's being used in chemical engineering and mechanical engineering, as in computational fluid dynamics. They have published on that. If you're interested, you can see it, but I'm going to show you the numerical reservoir simulation version of it. But let's first talk about the well-based part. And in the well-based part, I'm going to give you an example of a model. It's called, this is in ADNOC. Again, it was done in 2005. It was 160 horizontal well. It's a naturally fractured carbonate reservoir. The model that they had built, the model was built combined by Exxon, Shell, and BP together. It had 1,000,000 grid blocks. It took 10 hours on a 12 parallel CPUs HPC at the time that they would do that. And it required, we only used 12 simulation runs to build our full field model at Smart Proxy. And people at the time, people didn't believe us. They said you need at least 120, if not 1,000 simulation run. We only used 12 to do that. We have simulated the required Spatio-Temporal Database. All the details of that, I have published a book even on that. You can go and see how it's done. And we trained and calibrated and validated it. And after the validation, we required a solid and deep understanding of machine learning in order to do that. And we usually, at the time, we called it SRM, or Surrogate Reservoir Model. And what we did, we came up with 167 wells. And what they wanted to do, they wanted to know how they can increase production of oil without because they were injecting water as well, without water cut increasing. At the time, there was water cut for all the wells were very, very low, but they did not, part of the management did not want them to open the choke to produce more oil, because they thought they are going to produce more water and it's going to kill some of the wells. What they want us to do says, is it possible for you to tell us what to do based on the model that we have developed? We took all 167 wells, we divided them in 5 clusters using fuzzy cluster analysis after doing our modeling in what is called TDM today. And we came up with this conclusion. These wells that we identified as cluster 1 and cluster 2, we said these are definitely candidates to open the choke without any problem. You're going to get a lot more oil without any issue on the water cut. These wells, cluster 4 and 5, we told them don't touch it if you open the choke setting here, and rate relaxation they called it. If you do that, yes, you're going to get a lot more oil, but your water cut is going to go up so fast that you are going to lose the well eventually. I don't know how long it would take, but that was the outcome. And after cluster 3, we said depends on which wells in the offset you do, that's going to define what the cluster 3 is. What we told them, this was the ranked #1 well, the rate relaxation. As you see on the right-hand side, it says cum years versus rate cap and water cut. The water cut doesn't change at all. What you see on the left, you see the oil production goes from about 10 million to 25 million for 25 years. But no problem with water cut. The water cut actually goes down. The production stays the same, but water cut goes down because the oil production goes up. This was ranked #1 in cluster 1. This was an example of rank number 75. This was cluster 4. We told them don't touch it. Yes, you're going to get more oil, as you can see on the left, but look what happens to your water cut. It's going to go up to 75% eventually, and you're going to lose it. What happened after 6 years? They decided, after this project, they decided to take 20 wells and open the choke on the 20 wells. And they did that, and after 6 years, they looked back to see whether what we did was correct or was wrong. And what was interesting was the 20 wells that they opened the choke, they included all the wells. They included 1, 2, 3, 4, and 5, all the clusters. This was the result from cluster 1. What you're looking at is in the dark black is the cum oil production, and what you see in the green is water production, cum water production as a function of time. This is when they opened the choke as we recommended. So if they would not have opened the choke, this would have been the cum production. And when they opened the choke, they gained 1.6 million barrel of oil during that 5 years. Let's see what happened to water cut. This is water cut in percentage prior to opening the choke, and after that, less than 1% water cut, no change. This is another well. This was in cluster 2. Again, 1.9 million barrels in 5 years of oil production. Water cut, below 5%, no change. This was another cluster 2. What happened? 1.6 million barrels of, these are the one we told them to open the choke without any problem you're gonna have. Water cut never reached 3%. This is cluster 4. This is the well we told them don't open it because you're gonna have water cut that's gonna kill the well. Look what happened. From the moment they opened the choke, the water cut went from 2% all the way to 40%. This is another cluster 4. Prior to opening the choke, it was less than 5%. After that, quickly went at 30%. Another cluster 4. Prior, it was less than 5% after went to 30. This is cluster 5. Prior to opening the choke, as we recommended, it was less than 1%. After that, went to up to 50%. So, and the same thing is true for, this is what happened. For cluster 1 and 2, look at before and after maximum water cut. And look what happened to 4 and 5. So literally every single, out of the 20, the 20 predictions that we ever made were correct. And literally it added about $2 billion incremental oil production at $75 per barrel during that time. This goes to 1916 when it was, I'm sorry, 2016 that was finished. Anyways, so there's the other one is the cell-based. The way you do with cell-based, you take a focal cell, and this cell has 26 neighbors that you have to deal with. The first tier of neighbors are connected to the focal block through the entire plane, and you have 6 of them. The tier 2 are the ones that communicate with the focal block through a line. And since there is no communication through the line, it goes through the another, so it's a 2-step communication with the focal well. And there are 12 of those, as you can see. And finally, you have tier 3, and those are communicating with the focal cell through the point. And what that means, that means they take 3 steps before they communicate with the focal cell. And this is how you build the model for every single cell. And when you do that, then therefore each record may include static and dynamic information from 27 grid blocks, 26 neighboring and 1 focal one. And if you build your model based on tetrahedron rather than blocks like I showed you, no difference. You just have to deal with it in a different fashion. But the general idea is exactly the same. That's how we did it successfully in computational fluid dynamics. And another thing that you have to do, this I'm showing it in 2D just to clearly show this is tier 1 and 2, but you need to identify the distance with the reservoir boundary and distance with every injector and producer for every cell. And when you do that, you provide that information. You have to identify which parameters you have to use depending on the data you have. And you train, you calibrate, and you validate your model. And then the smart proxy model is validated against a series of blind numerical reservoir simulation runs. So if you take 10 or 8 of them to build the model, then you go back and ask your client to go ahead and make another run in the same range, but make any changes that you want, static or dynamic, doesn't matter. Make any changes you want, give me the results, and I compare it to, and I'm going to build another reservoir simulator model, the smart proxy, and give you the results of mine, and you can compare. This is an example for SACROC, actually, one of my PhD students, Vida Olami, did. And you can see that the pressure on the left, the pressure from numerical simulator, and on the right, the pressure is from smart proxy that she built. And on the right, you see the same thing on saturation for a given grid block. The same thing, another PhD student of mine, Shura Annie, who's working right now for Halliburton, did her PhD on this. She did that for CO2 in Otway, Australia. This is the way the system was built. The geology of it was quite complex, and you can see on the left the numerical simulator, and on the right the smart proxy for different layers at different time. This is the pressure for a given layer, and you can see the result, and you can see how direct it was. This is the saturation for one of the layers at different time. You can see on the left is the numerical simulator, on the right is the smart proxy. And this is when you do the same thing, top on the pressure, bottom of the gas saturation. And the left is numerical simulator, on the right is smart proxy for a given, this is pressure and gas saturation distribution for a given layer at a given time under certain circumstances of how much you're injecting and how long you're injecting it for. And you can compare these two and see how good the smart proxy can do this. more examples of that. That pretty much covers this. I think we have covered this. We went through a whole hour. I don't know if I should stop or I'm going to take another. Let me take another 5 minutes to just go ahead and show you the shale analytic part. I probably can't finish the dynamic shale analytic, but at least it gives you an idea. The shale analytics literally uses artificial intelligence and machine learning for shale, for unconventional resources, and it's significantly different from traditional modeling, the numerical simulation or rate transient analysis. The traditional modeling applies to shale. It includes incredible amount of assumption, a lot of guesswork. It hardly uses the reality, and it uses what's called soft data. Here, you used hard data. The soft data literally is assumptions, things such as fracture half-length, fracture width, fracture height, fracture conductivity, stimulated reservoir volume. It's all guesswork, it's all assumption. There's very little reality to those. What is hard data? Hard data is everything that you measure, from well trajectory to well construction to, okay, let me see if there is a chant. David is telling me that we have 2 hours of Zoom time. Take whatever time you need. Folks can get off anytime. Thank you very much. I will do that. Then I'm going to take a little slower to complete this. Thank you very much, David, for mentioning that. So I'm not going to go very fast. I'm going to go try to cover this. So in the hard data that is used in shale analytics includes, as you see, well construction and trajectory from measured depth to true vertical depth to well location to inclination and azimuth and deviation to formation characteristics from a lot of well logs is used, and thickness, porosity, TOC, water saturation, frac gradients, bulk young, and shear modulus. If it's available, if you have everything related to seismic, if you have available, you can use it and so forth. Then you have completion design. This is the design that it's made, the lateral length, the number of stages, the number of clusters per stages, the shot density, the cluster spacing. Then you go to hydraulic fracture implementation. They combine, some people combine this whole thing together as completion, which is perfectly fine, but I separate them because they're different, really. Completion design is what you do prior to implementing the hydraulic fracture. Hydraulic fracture is done when you are really doing the completion. And a lot of time, whatever you design, it may not happen because there's characteristics of the rock that tells you what you can inject, what you cannot inject, your pressure and rate and all of that. So I separate them, the fluid type, the amount of the fluid you use, the amount of proppant you use, the type of proppant you use, what part of it, what percentage of it is fine, what percentage of it is coarse, what is the proppant concentration, how much clean volume prior to just clean volume is what you break the rock before you inject the proppant, and what is the slurry volume, what is your injection rate, the average, the max, the min, what is your injection pressure. So these are the hydraulic fracturing implementation. And next is what's called well spacing and stacking. Well spacing has to do with the space between the wells in a given pad, and also when you, the closest to the next pad that you have, the distance between the child and parent well. And then you have space between wells, and you have vertical distance. For example, in Permian Basin, you have Wolfcamp A and B. So that's called stacking. So the distance between these different wells, whether it's the same pad or not, usually they're not. And are these, what is the distance, vertical distance from each other, or the distance from this X, Y, and Z? You have to take all of that information. Then you come with operational condition. You need to have the choke setting and casing pressure and tubing pressure, and sometimes even flow line pressure, everything you do in the surface that interacts and impacts the production. And then you need oil, gas, and water production. All of this data is available in Shale, as we dealt with a lot of projects for many companies. And you can see the results actually. Before we go forward, one of the things we see when you look at the actual data, for example, here, in the next several cases that I'm going to show you, on the y-axis you have the rich gas 12 months in this is for Marcellus Shale in southwestern Pennsylvania, and every dot identifies a particular well, and in x-axis here you have clean volume. And it tells you how does these two correlate with each other. You tell me if you see a very clean correlation here. This is the actual data. What do? We use fuzzy cluster analysis, and we divide the production based on poor, average, and good, as you can see in the bottom and the colors blue, yellow, and red in terms of the value of the 12-month. If a well produces so much, it's a poor well in 12 months. If it produces so much, is average. If it produces so much, then it's a good well. But the key is they do not separate with each other based on a certain barrel of oil or MCF of gas. Right? So if the differentiation is they overlap what's called poor and average. That's the fuzzy set theory. That's how human brain deals with data, and we're trying to model that. When you do that, then if you look at that, look at if you divide your all the hundreds of wells that you have here into three categories of poor, average, good, not based on clear clusters or statistical cluster, but on a fuzzy cluster that they overlap each other, then can you tell what is the clean volume for poor wells, for average well, for good wells? And what you see, the background red, the pink background, that's the average for the entire, all the wells combined. But then you have it for poor and for average and for good. And do you see a pattern? It's very, very clear. The next one is, what if it's the same data? What if instead of dividing it in three categories, what if you divide it in four categories? To poor, average, good, and excellent. You still see a pattern. What if you divide it to five categories? Poor, average, good, very good, and excellent. Or you can name it however you want, as long as the value of the production is different, but they overlap. Do you see a pattern? So this is called pattern recognition. You've got to, and then if you optimize the number of patterns and the number of the categories, what we call is fuzzy pattern recognition. From fuzzy clustering, you go fuzzy pattern recognition, and this is what you see. The actual data here is shown in the gray, and the pattern, fuzzy pattern recognition shows in blue or purple dots. So the question is, in the purple dots, do you see a pattern? Is there any doubt that there is a pattern? By the way, this is not a statistical correlation, folks. This is not Windows. This is fuzzy pattern recognition. It is very, very different with what people do using statistics. Now, that said, I'm going to show you exactly the same results for different parameters and see what happens. This is stimulated lateral length versus 12 months of production. Do you see a pattern? If you show this pattern to your boss and you say you want to get more lateral length, do you think he agrees with you? But what if you show him this? Is there a pattern or not? The good wells have higher stimulated lateral length than average wells than the poor wells. And you increase the category from 3 to 4 to 5, do you still see the pattern? And when you go for the entire system, do you see a pattern? So if your boss sees the purple line, would he agree with you to increase the stimulated lateral length when compared to see the actual data? So the actual data includes patterns that you should be able to generate. This is the longitude. You can see a little pattern actually in the real data, but this is when you do 2, 3, 4 categories and for the entire system. The same is true for measured depth, 3, 4, 5, and for the entire system. This is for total amount of proppant. Look at that. When you do 3 categories, when you see 4 categories and 5 categories, do you see a pattern? I think it's very, very clear that you see a pattern. And you can make a judgment on that. By the way, this is prior to building a model. We are not building a model. This is what we call descriptive analytics. We try to make understanding of the data to find out which one we should use in order to build our model. This is total number of stages, 3, 4, and 5 categories. The higher number of stages, the higher the production. So when you do that, then you use the KPI, the key performance indicator, using fuzzy pattern recognition, and you can identify which parameters, because a lot of time you have a lot of data, but you don't have millions of wells. So you cannot use 500 inputs to build your model. It doesn't make any sense. It memorizes everything immediately. Therefore, it's called the curse of dimensionality. You have to make sure that you use enough data. The number of wells you have, the number of records you have, determines how many variables you can use in your model. And when you do that, it can identify, if you identify the output, which is here, is 30-day production of cube condensate, it tells you for that which parameters are higher value than the other one. If you change that to 180 days of cum gas, then you see there is some differences. So you have to do that for all of them in order to finally make a decision that which parameters you're going to use in order to do that. Here, I need to mention one thing that in our research at ISI, recently we came to that conclusion. It's not 100% completed the research. We will publish it, and again, we share it with everybody as we move forward. One of the things we are learning that AI and machine learning that is applied to reservoir engineering, modeling, and management, you should not use the same approach that is used in big data. You should not use the same approach that you use in non-engineering problem. Because if you use Python, or if you use the software that people have generated, if you use TensorFlow, if you use PyTorch, if you use scikit-learn to build these models, then where these libraries were developed for, were they developed for engineering? No, but they were developed for big data, for non-engineering, as we talked about it. If you use it for the engineering related problem, you find some detailed issues that are associated with it that right now we're doing research on. To be very, very honest with you, it surprised us. We are not 100% sure yet. We're still doing research to confirm what we have come up with. For example, we found out that Atom, that is used as a gradient descent approach that these libraries have, it works for big data, it works for non-engineering, it works for image recognition, but when you use it for reservoir engineering, it has some really big issues. And you have to identify, you have to address them. You may want to use another technology. Why? Because characteristic of those algorithms sometimes do not correctly apply to what you're working with. It has to do with the type of data that you have, the amount of data that you have, the amount of variables that you're dealing with. In data partitioning, for engineering related problem, you need 4 partitioning. When you use Python or R, you only get 2. You get training and testing. That's why a lot of time it doesn't work. You need to divide your data first to 2 partitions. We call it development partition and blind validation partition. Blind validation partition is not used to train, to calibrate, or to validate your model. You put it aside. You pretend you don't even have it. And sometimes your client does that, doesn't even give it to you. Great. That's a very, very positive thing. But the data that you get, but you don't know if they do it or not. So you want to put it aside because your model has to confirm so you can be successful when they do that. So your model development, then you divide that into 4 partition of training, calibration, and validation. I have done that in the past. I provided some details on what I mean by that. But another characteristics of this algorithm that's different from conventional ways of doing AI and machine learning when you do it for non-engineering application for big data is what's called today explainable AI. Characteristics of those algorithms sometimes do not correctly apply to engineering because they're black box, as some people call them. We do not call what we do black box. Why? Because it's fully transparent. You can clearly see the model that you develop. What does it do? It's explainable. What's called explainable AI, XAI. I'll give you examples and show you results in a few minutes. So what we do, we take the input after we did what we mentioned to keep KPI, we identify which parameters we're going to use. We go through hyperparameters, we build our models, and we get the output. Now, what I'm going to show you is developing the predictive model that learned from field measurements using AI. And what I'm going to show you is the Shale Analytics that has been applied to that fourth part of the data, the part of data that blind wells that was separated and was not used to build, train, and calibrate the model. These wells, we didn't even have it when we built the model. Afterwards, we compared them to the model that we built, see how good our model can predict. Here's an example. This is from Marcellus Shale. We have 73 blind wells. Again, wells that were not used. The data from these wells were not used to build the model, to calibrate the model, or even sometimes to validate the model. It was afterwards. The R-square is about 0.79. The correlation coefficient is 0.89. What you see in blue, every single dot is 30-day cum production for a single well. And what you see in orange is for the same well what Shale Analytics predicted from the measured data. And you see how good it was for the 73 wells at 30-day cum. This is the same. Now we have a smaller number of wells because they're not all the wells produced for a whole year yet. This is 58 blind wells. R-square of 0.82, correlation coefficient of 0.91. And that shows you in blue the actual field measurement, and in orange what Shale Analytics does based on what we just explained. This is Utica in Ohio. 59 blind wells for 360 days cum oil production, R-square of 0.84. This is for the same. We have 86 wells with 180 days of cum production. The R-square 0.86. These are blind wells. None of these wells, data from none of these wells were used to build the model. This is Niobrara in Colorado, 51 blind wells, R-square 0.85. This is Eagle Ford. One of the Eagle Ford, we did multiple projects for Eagle Ford for different companies. This is one of the companies. This is 113 blind wells, 360 days cum on the y-axis, and the R-square is 0.83. This is Wolfcamp, Permian Basin. We had 120 blind wells for 180 days of cum production. You have the predictions, as you can see. Correlation coefficient 0.93. This is Wolfcamp again. Here we have a whole year of production, almost 0.8 R-square in Wolfcamp, Permian Basin. So we're talking about explainable AI. How do you explain how AI works? Well, how can I explain to you what I have done? When you ask a question, I answer it, correct? So the question is, can't you do the same thing with the model you built? An explainable AI is an AI that when you ask a question, it should be able to answer your question. What if I ask the model that I built for Permian Basin, let's say, and I ask them, okay, how does the formation thickness and lateral length combined impact production from these wells? If you ask that question from your AI, you're not asking about a particular well, you're asking the model's behavior. This is what it's going to show you. This is going to explain to you that as you go from lateral length from 1,500 to 5,000, when your net thickness is 90 feet, this is how the production is impacted. When you increase it to 100, the blue. When you go to 110, then you have the green. When you go to 120, okay, there are at least 10 to 15 other parameters involved in there. In order to be able to explain it in a plot fashion that people can see, then you have to take every other parameter and make it constant. And you can change it to whatever you want. You have full control. You can change every single parameter of every single well and see how it impacts your output. Then the question is, does this make sense? Do you remember type curves in our industry? When we do type curves, they're very well behaved. Why? Because they are based on equations. That's why they're very well behaved. This is very well behaved, but it's not based on equation. What does that tell you? That tells you the physics have been modeled reasonably, in a reasonable fashion. That's why the behavior is reasonable. This is number of cluster per stage as a function of lateral length. What is the result is for, this is for the entire field. You can do that for every single well. You can do that for a portion of the reservoir. This is lateral lengths in x-axis, and what you have in different colors is proppant per foot, 400 versus 1,000 versus 1,500 versus 2,000. Does the curve make sense? Question, if you do a statistical analysis, if you do regression, do you get the same result? I promise you, no. I will be publishing another paper to show you the difference. Exactly the same thing. If you do it with multi-variable regression, then what you get is a complete nonsense curve. Why? Because it has nothing to do with physics. In statistics, you do not use physics. You don't need knowledge. You don't need domain expertise. That's why they tell you that at the beginning, 10 years ago, they told you don't feed your children with egg because it's going to increase their cholesterol. It's going to be bad for them. 5 years later, they said, oh, do it. It's fantastic. Why? Because it was purely based on the statistics. And then when they get the result, then they go to expert and they ask them, can you explain that to us? Depending on what the result is, I can explain it, but you get two different results. There's going to be two different explanations. That is the main difference between them. That's the difference between explainable AI. This is in southwestern Pennsylvania Marcellus Shale. What does that tell you? It tells you that change in azimuth is not making any difference within the range, of course, that we're dealing with in the production when you plot it against stimulated lateral length. How about average injection pressure? Look at the difference. It's very well behaved curves. This is explained. How about cluster per stage? Don't forget that everything that I'm showing you is done by AI and machine learning. However, it's going to be different for different fields, for different number of wells you have. It extracts the physics out of the data that you have, and it shows it to you in this fashion. But it doesn't mean this is gonna, if this is for Marcellus Shale, for cluster per stage against the stimulated lateral length and production, doesn't mean this applies to Permian Basin. This is percent of fine proppant per stage. The key, what I'm showing you here, is the well-behaved curves that are generated by AI and machine learning. And these well-behaved characteristics explains what is happening. And then, of course, you can take these and optimize the production by modifying those characteristics that you have it, because there are two sets of characteristics here. On the top, there are characteristics that there's nothing you can do about. If you're drilling a well in a particular location, there's nothing you can do about TOC and net pay, porosity, water saturation. You have an estimate that what they may be. You can change only azimuth and inclination, but then you can change the lateral length, the number of stages, the shot density. These are the completion. You can move them, and you can see how does that impacts production. And this is the process through which you do optimization for every single well, completion optimization to get highest amount of production. That said, I'm going to cover one more thing before we stop and answer any question that you might have, and that is dynamic shale analytics. The dynamic shale analytics is the AI-based simulation and modeling of unconventional reservoirs, resources. The idea is, can it predict frac hit and mitigate and manage, allow you to mitigate and manage? Let me show you some results that we have got. This is result from two of my master's degree students. So what is frac hit? If you have a parent well that you have multiple stages and multiple clusters, and let's assume these are the hydraulic fractures that went through. It's just all over the place. It's very, very tough. It has to do with natural fracture that exists. If this is the parent well, then this would be your oil and water production, and what you see in the gray is what some people call stimulated lateral length, but there is no way to know what that is, by the way. This is just an example. If you do the child well, and then which has a certain amount of distance from the parent well, then you do hydraulic fracturing for one of the stages, it may actually impact the parent well. This is called the frac hit. They communicate with each other, the interference, and the water that you're injecting in the child well to do the hydraulic fracturing is going to be produced by the parent well, and your oil production comes down. This is what people have been calling frac hit. This is what's really, really impacting shale production, oil and gas production from shale in our industry, simply because as long as we were having these wells to be too far from each other, nobody would never impacted anything. But starting a few years ago, as the distance between wells decreased because we were producing more production, this is what happened. So what did actually, how does traditionally in today, the current industry practices, how do you try to identify whether frac hit is going to happen or not? Well, they use a terminology which is literally the only thing it is distance between the child and parent well. They call it cutoff distance. And they say if the distance is less than a particular number, if that is true, then yes, you're going to have a frac hit. If it's more than that, if the distance is false, is not less than, let's say, 1,500, then it's false. Then you're never going to have a frac hit. But then they brought in the next item, which is on plane. They said, okay, it has to do with the fact that whether it is these two frac hits are on plane or not. On plane is when the parent well is within the frac plane of the stage being completed in the child well. And they said, okay, it's not only the distance, but the on plane as well. If they are on plane and they are less than cutoff distance, then there's a frac hit. Otherwise, there's no frac hit. So literally, they provide the four possibilities, three of them, you're not going to get a frac hit. One of them, you're definitely going to get a frac hit. That is how traditional frac hit modeling in our industry works right now. They did that for a while, and they figured out, no, things are going to get very, very complex, and they added something I'm going to tell you in a second, but let's just go ahead and look at this frac hit with on plane. As you can see, you have a parent well, the well's distance is about 1,000 feet, and then you do a child well, and you start staging it in different stage, and this distance is certain amount, And of course, as you can see, the stage 1 and 2 here in the well being frac are in the same plane, it's on plane of the offset. Therefore, here's when the frac hit is going to happen. This is the definition of this traditional 2 variable cutoff distance and on plane characteristics that is going to identify whether it's going to be frac hit or not. So when they did that for a while in our industry, they found out that, yeah, they are sometimes correct, but a lot of time they're incorrect. So after a few years, another thing was added. So this is what we had, cutoff distance and plane, as we said. Then they added another piece. And another information is whether the well that is going to be hit by frac of the child well, is it shielded or not? What does that mean? Well, shielded is defined that the parent well is protected by another producing well between itself and the child well. I'll show it to you in a second. And it says if it could be shielded or not, correct? And they come to this conclusion. If it's not shielded, but it's on plane and it's less than a certain distance, then definitely you're going to get a frac hit. And every other case, you're not going to get a frac hit. That is what today, traditional frac hit modeling in our industry is done. I call it traditional frac hit modeling in our industry. And this is how it's explained. This is the series of parent wells, let's say 1,000 feet from each other. And the red here, I'm going to look at whether the well in the red is going to be frac hit by these stages of child well, where you have the blue well is shielding it actually. So itself is going to get hit rather than the other one. But in reality, you'll find out that even the red one get hit. That's how they came up with this idea of shielding. So one of my grad students, Ryan Tyree of Range Resources, he did his master's degree with me while he was doing he was a completion engineer. He's now a top completion manager there in that industry. And he brought in the data that he dealt with using the software from ISI to do this master's thesis. And what he did, he had about 1,000 examples, 959. 250 of them, the cutoff distance was less than 1,500, 26%. 300 of them, about 32% of them, were the distance between the parent and child stages was between 1,500 and 2,000, and 400 of them were between 2000 and 2005. Look what happened. On the left, you see the number of the wells, examples that we have. On the right, you see the percentage of frac hit. So it says when there's 249, when the distance is so low, less than 1,500, you can see that when it's 51% frac hit you have when the distance is short. When the distance is in the middle, which is about between 1,500 and 2,000, we have 300 examples, we have 30% frac hit. And the distance goes above between 2,000 and 2,500, which you had 400 examples, only 10% of them get frac hit. Makes perfect sense, doesn't it? Now I'm going to show you exactly the same thing in more detail. This is the number of cases. We have 1,000 cases, right? But here it shows you the distance between parent and child. Instead of dividing it into 3 categories, I'm dividing it into 20 categories. And you can see that when the distance is about 780 feet, 75% of them get frac hit. When the distance is about 1,056, you have 59 cases. You have more than 63 cases that get hit by frac hit. When you go to this distance of less than 1,000, 87% get frac hit. Then you go to the second part, which is the distance between 1,500 to 2,000, and you can see the frac hit goes between, the average is about 30%, goes as high as 45%, as low as 27%. And we had a lot of examples with the distance was from 2000 to 2500, and you can see it's the maximum is 16%, minimum is 6%, almost 10% frac hit. So this is the data that we had, that we dealt with. Let's look at how the traditional technique that people have used worked. So remember, we have 4 cases when you have on plane and shielded. In reality, when you had on plane and shielded, of course, this is what we're dealing with when you had less than X, the distance was definitely there. But if the distance is less than XCD, the cutoff distance, you're going to get a frac hit. In reality, you're going to get frac hit 17% of the time, and you're not going to get frac hit 82% of the time. But the traditional technique says, no, you're never going to get a frac hit. 0 and 100% is not a frac hit. If you are not on plane but shielded, the traditional technique still says you're never going to get a frac hit. The reality is, yeah, you get 5% frac hit. But if it's not on plane and not shielded, this is another time that traditional technique says you're not going to get a frac hit. And in reality, with the examples we had, only 3.5%. So the highest is 17–18%, the lowest is about 3% in these cases. And the traditional technique says no frac hit versus complete frac. So look what happened here. This is when the traditional technique says you're definitely going to get a frac hit. When you are on plane, but you're not shielded. In reality, you're going to get 65% frac hit and 35% not frac hit. But the traditional technique says you're always going to get a frac hit. So you see the difference between the traditional technique and the reality for at least this 1,000 cases that we have. Now let's see the exact same thing from, so this is usually what happens most. The highest possibility of actual frac hit, most often in the actual field, is this part B. This is actually caused the whole thing behind bringing out this problem. What happened to Shale Analytics? Let's look at the result. Again, the blue is exactly the reality, and this is how the frac hit. We published the paper. This, you can read it in all the detail. See how we did it. You can clearly see, and you can see Ryan Tyree's master's thesis has all the details, how we did that. 82% not, Shale Analytics says 88%. Or when frac hit is 17%, it says 11% looks correct. In this case, Shale Analytics says 0% versus 5.1, 100 versus 9. In this case, almost the same. In reality, it was 3%. Was correctly predicted by Shale Analytics. But the most important one is this. Remember, in traditional it said 100 and 0. The reality was 65 and 35. Look, the Shale Analytics, 63 and. So that was how Shale Analytics was able to do that. This was my part of analysis. In his master's thesis, he can show you, Ryan Tyree, that the blue is the Shale Analytic model that he developed, and the green is the actual possibility from the traditional techniques. So when you are less than 1800 distance, industry standard give you 70% correct, 90% well, Shale Analytic give you 90% being correct. When it's more than 1800, the industry standard gives you only 50% of time correct, but Shale Analytic is correct 90%. I'm going to finish this just to show you, but this is not dynamic Shale Analytics. This is Shale Analytics, but then you have to combine this with top-down modeling. We perform top-down modeling, and one of my PhD students, Sudab Ismaili, who I think works for Exxon right now, she did this during her PhD thesis at WVU. She built using Imagine software at ISI's Imagine software that is provided to the university. She used that in order to build a top-down model reservoir simulator for 160 wells in Marcellus Shale, and the forecasting was blind. It's for the entire field, and of course, we developed for every single well. When she was finished doing that, after the model was finished, and we found out that Marcellus Shale, that's the company we're working with, had developed more wells, and we went ahead and they gave us the data. I mean, I didn't do that. Sudhava did. She used the model she had developed and compared it with the actual data that was provided for the company for these same path, different wells. And you can see the result. The dots are actual data, and the line is the model that Sudhava was developed. This is for one of the paths, that's for another path. So that there's another thing is we have a little more time. So let's talk about petroleum data analytics. Actually, I'm going to have a complete webinar in August 19th on petroleum data analytics for SPE. This is only a few slides. The definition of petroleum data analytics is the application of AI and machine learning to oil industry in general. It includes data analytics and it includes big data analytics. There is a difference between these two. And that's one of the things people have to understand, that reservoir engineering is not big data. So you should not be using that approach. There's difference between them. So data analytics using current existing data to build models, optimization of decision making, and big data analytics using real-time data. This is applicable for drilling and artificial lift to a lot. So let me explain it to you. If you take that petroleum data analytics and divide it into big data analytics and data analytics, then in data analytics, you can see reservoir engineering, completion engineering, and you have these examples: workover, hydraulic fracturing, completion design, well testing, core analysis, operational constraint, historical injection, and all that information needs to be built model. For big data, you can go to drilling engineering, to production engineering. MWD and LWD for drilling, distributed acoustic sensing and temperature sensing. Right now we use it for, that could be used for big data analytics, the SCADA and ESP, the seismic attributes, because you have incredible amount of data here. And something that goes in the between them, it could be well logs or artificial lift. Both of them works here, depends how much data you have. One last thing that I would like to add, that the engineering application of AI in our industry could be purely data-driven modeling. And that's what I mentioned to you. It requires explainable AI to honor the physics. And the requirements is engineering expertise, AI expertise, honoring the physics, validation of the physics, and development of intelligent agent to do that. This is what I showed you overwhelmingly today. Another thing that I showed you was smart proxy modeling. That's all of this is purely database and purely it's physics based, but the data from this comes from numerical reservoir simulator. So you can clearly see that this technology can model the physics. This is the physics that you modeled. You know everything about it. And smart proxy provides you very, very high quality and high accurately value. Why? Because you can just solve. However, it's using equations. Now these two are separate. You should not combine them together. That's one of the key things that I'm so mentioning, that you should not be using. If you want to use AI, and you should not be using so-called hybrid model. Do not combine these two together. Why? Because when you use purely data-driven modeling, it gives you a complete different approach to problem solving. But physics-based smart proxy proves to you that it can model the physics. as long as you have the data. But when you combine these two, literally, it no longer have anything to do with AI. It shows those who do that, they're combining the data with equations. This is, to me, a lack of expertise in engineering if statisticians do it, or it's a lack of expertise in AI if engineers do it. There could be reason because of the lack of transparency. They don't tell you why they're doing it, or it's just a marketing scheme, or it has nothing to do with reality. It's a very bad idea in my opinion. One last thing I want to show you. A lot of buzzword and going on today in our world with this. So what if somebody tell you that you can be a master engineer in just 1 month? Master reservoir engineer. Do you believe them? What would be your reaction to that? What if they tell you they can make you a master physicist in just 1 month? Well, the reality is nobody says that. This is not real. No company has ever done such a marketing. I just made this up to ask you whether it makes sense. Is it possible for you, or do you believe it if somebody said, I'm going to make a master statistician in just 1 month? Does that make sense to you? None of this is true. Nobody does that. But you know what they do? This is a real marketing advertisement that I came across with, and to be honest with you, it shocked me. If people call themselves master data scientists, because why? Because they went to this company and took a 1 month course online. That is a very sad thing, unfortunate, but that's the difference between reality. So thank you very much for your attention. That completes my presentation. If there is any question you might have, I have here answer 5 questions that I will go ahead and look through and answer them. One question says, how does the time resources to model using petroleum data analytics compares with current accepted method, reservoir characterization, numerical simulation? How does the time are used? Well, the way in petroleum data analytics we use time. Again, what's the difference with numerical reservoir simulator? The key is the reason we were able to build TDM was because we have been building numerical reservoir simulators for 25, 30 years. So what we learned from numerical reservoir simulator, we brought it in and to see how we can do it with TDM. And one of the things we learned that you need to bring in time step. So we take all the information. There are 2 sets of, you have dynamic information and you have static information. Static information, some of it even change with time. Not the porosity doesn't change with time, stays the same. But porosity that impacts the production, it's going to change as a function of time when you put an average value that is that is calculated as a function of kriging and interpolation. Because when you do it and you have only 5 wells, the estimation of porosity in a new location that you don't have a well is a value. But when you have in the same place you drill 20 more wells, and now you have 25 wells, then in the exactly another location that you don't have, now you have a different porosity. Why? Because you have more information to generate that porosity. That's called polygon-based porosity, which we call it dynamically modified static information. It's in the book. I've explained it. So that's that. But in the dynamic data, and the data that we use as injection data, wellhead pressure data, all of that, then you use it as a time step, and you use you have to use it for some of the operational conditions should be used for the same time, but offset producers should be used as a time step prior to that. I hope that answers the question. I'm not sure. The next question is, how easy or hard is it to extend the subsurface model capability to the entire surface infrastructure? Very good question. Actually, not that hard. We did develop for BP, and we developed it many years ago. We published it. We used a purely data-driven model to build a model of the complete surface work that they had. So it is possible to do. There's a lot of publication. If you send me an email, I can send you the publications. Will the recording of this webinar be made available? I don't know. I don't think it has been recorded. Correct me if I'm wrong, David. The next question is, how do you differentiate between engineering and non-engineering problem? I explained that at the beginning of this. If a consultant had used TensorFlow for your model, how do you enhance the model? Okay, so that's again, these are two details. Right now, you can use TensorFlow to generate explainable AI. Don't get me wrong. Why? Because it doesn't have to do with the algorithm that is used for the library. Okay, it has to do with how you use the data and that algorithm. What I mentioned about TensorFlow and PyTorch and scikit-learn and all those is that recently we have come to conclusion that not all, but some of the most common algorithms that they use for gradient descent, it is possible. We haven't completed it yet. We'll publish it as soon as that research is completed. We have come to conclusion that if it's not applied to big data, then you may get a lot of wrong results. And the reason behind it, I cannot tell you right now because we've not finished our research, but as soon as we do that, we publish it. So that's a different story. It's a difference between big data versus non-big data. And as far as engineering and non-engineering is depending, it has to do your understanding and your knowledge of the physics problem that you're trying to solve. Use that knowledge in order to be able to build your model or treat your data in a way that makes sense. How can we use the data analytics in forecasting phase where we do not have any historical experience? It's not going to work. TDM, for example, you cannot build that's a very, very good question. TDM, if you build a TDM and history match it with primary production, you cannot use that model to tell you what happens in EOR. You have to wait until you get some EOR data and then you build the model. The only way we have done that is through smart proxy. So you build a numerical reservoir, because you can do that in numerical reservoir simulation. It's estimation, but you can do the analysis. You can build it in an EOR from a history match the primary production without EOR, but do the EOR in the numerical simulation. And the good thing about smart proxy is you can build a numerical simulation for EOR, but then you can run it 10 million times using smart proxy in order to come up with a potential possible solution, because you can do uncertainty quantification, you can do optimization. Nobody says it's going to be right or wrong because it depends on how good your model is, but you can do that. I think he's asking, how long does it take to produce result using one method versus the other? Okay, the amount of time it takes to build a numerical reservoir simulator for a mature field in reality literally could go multiple years. Many places that I have dealt with and interacted with, not in academia, but in real world, it takes them about 3 years to go from phase 1 of the geological model to phase 2 of the geological model to phase 3. Almost 3 years for each geological model to build. That geological model is provided to reservoir engineers. Reservoir engineers build a numerical reservoir simulation, use the geological model as the basis, But what happens, it never works, right? The base model is never a good history match. Then you have to change, and we are reservoir engineers, we never make mistakes. So if you don't get a history match, it's not our fault, it's the geologist's fault. That's what we say. That's what we have been saying for the past 70 years. So what do? We modify their reservoir geological model in order to get a history match. This whole process can take as little as 1 or 2 years, and in reality, when it's real, it can take as much as 3 to 5 years. You can build the TDM in 3 to 4 months, if not shorter. Can you really forecast production? Of course you can. Production, I just mentioned it many times. Luis Acosta, on explainable AI, you mentioned curves obtained are well behaved as opposed to multivariate regression models. Yes. Can you comment on how was this achieved? Yes, it is achieved because when it well behaved, what does that tell you? That tells you the physics that it was trying to model, it did a good job. The physics is modeled. Isn't that what you say when you do a mathematical equation to model the physics? And then you generate type curves and they're beautifully behaved, very well behaved. So you want to use, all I'm saying is use the same logic to judge this one. If it very well behaved, no equation was used, but it's still very well behaved. What does that tell you? Apparently understands the physics pretty well. Can TDM account for new wells in the conventional? Yes, it can, definitely it can. The infill location is one of the things we have done. I showed you one example for one of the companies, but we have done it multiple. And the answer is yes. And again, in the book, it explains how to do that. How easy and hard is it to apply the same capabilities you have presented today to the surface infrastructure paths? It's quite possible. When you do that for subsurface and you get good result, you generate a big understanding of how you should. That's why we were able to apply this to the computational fluid dynamics. We published it, and I showed a lot example of that, and I can show you. Actually, we're publishing the book soon on that. I can, if you send me an email, I will send you some papers and some link to see it. It is mechanical engineering and chemical engineering. So what we did, we are engineers, we understood it. So what we did, we brought in people from DOE, Department of Energy, US Department of Energy, and ETL, and they were experts in mechanical and chemical engineers. We worked together and we were able to solve that problem. And we were engineers, so we understood some of the things, but they were expert in that particular area, so they could ask all the detailed questions that we had. They could answer all the detailed questions that we asked. And our literally 25, 28 years of experience with AI and machine learning helped us what to do, what not to do in order to be able to model that. So the answer is absolutely yes. The question with how easy and hard is to apply this technology to surface facilities, which is you can use. We actually did that. I just published the paper. We did that for to estimate deep what happened in Gulf of Mexico by BP, the explosion that took place. We used exactly this technology in order to identify how much oil is being extracted into the ocean. And BP was saying 1,000, and it says 5,000 barrels a day. We came up with 57,000 barrels a day. That President Obama mentioned it in one of his interviews on TV. And then when they measured it, it was 57,000. I have published that, and you can see it. Where does a reservoir engineer start to become a knowledgeable? You've got to learn AI and machine learning and just keep practicing, and you make mistakes, you get bad results. Don't feel bad about it. That is the key issue about research. You never do one thing and you in SPE Connect, there are people who say, oh, I used a neural network once, 10 years ago, it never worked, so I threw it out. Well, that tells you about their understanding of the technology. It's not 1 or 10 or even 100 times. You just learn how it works, and a lot of work we have to do. But it's you. If you, I have students that were very successful. I have students currently that I'm so proud of what they do. I'm learning from them sometimes. That. So next question is, dear Professor, in the specific case of pattern recognition, does machine learning algorithms solve problems related to classification based on facial properties despite the queries of scenario? Example of face. To be honest with you, that's a little too much of a question for me to answer. That we have 2 hours gone. I would be happy to give you my opinion about that. It is, to me, as long as you're a domain expert and you understand and become a good practitioner of AI, then the answer should be yes, you should be able to do that. TDM cannot predict what has not been observed correctly. That's correct. Trained on the primary production data cannot. That's correct. Okay. And says, does that mean that in practice we still need both TDM and traditional numerical reservoir simulation? The answer is absolutely yes. If so, what is your advice on splitting our time between the two approaches? Don't 50-50. Study them both, and I'm sure you will enjoy it very, very much. But yes, it's very, very correct what you said, and I agree 100%. With that said, I think that brings us to the end. We're 2 hours right now, and thank you for attending, and let me know if there's anything I can do in the future. Have a great day, and Dave, with your permission, I think we will call it a day. Am I correct?
Yes, thank you. Thank you for everything today.
Thank you so very much. Have a great day. Bye-bye.